Hello kids, today we're going to discuss how Faraday's law works for electromagnetic induction, how current is induced in a coil with the help of a changing magnetic field. So this is the Faraday law simulator in FET simulations. I'm going to attach a voltmeter to it to see to see the direction of the current as well as field lines for the magnet, right? I'm just going to change the polarity. Now as I said, current is induced in a coil, in a solenoid, when magnetic field changes through it. So if I move the magnet slowly, as you can see, there's a tiny little fluctuation in the coil, right? And small currents are being produced, as you can see. Now, if I do it faster, then the glow is quite bright, right? So if I do it slow, then there's not much of a voltage. And to note the fact that the point where more electric field lines are crossing, the amount of voltage generated is greater compared to the points where field lines are less, right? As you can see, the field lines are now. This also to be noted that the field needs to be perpendicular to the circular motion of the current in the coil. So if I just move the magnet like this, all right, there's very few points at which that 90-degree angle is satisfied and you get voltage, but it's very little. But if I do this movement at this point, there's huge amount of current being produced, right? And even in the middle, as you can see, there are points when voltage production is reduced. So just play around with this simulator. You'll see how current is being generated in a coil using a magnet, a bar magnet, right? Now I will give the details of what is actually happening. When these field lines, when these magnetic field lines cross the solenoid, they push the electrons inside these conductor coil, and they push it or give it energy to go through the circuit, and which we can detect with the help of this voltmeter as well as this light bulb, and the loop keeps on continuing. If there is no load attached to this, then you won't be able to see the the current going through this coil. Why? Because current only flows through a closed circuit and not through an open circuit. So if this was an open circuit, no matter how much I move the magnet in and out through the coil, you won't see any deflection because the circuitry is open. For this case, the circuit is closed, as you can see, from one end of the coil connected to the bulb and as well as a voltmeter, and loops all the way back to the other end of the coil. So it's a closed loop, and once I push the magnet through it, the electrons are pushed. And also note the factor that the polarity of the magnet decides which way the current is going. When I push the north through this, then there's a negative, and when the south is going through the coil, is this. But if I move the magnet the other way around, it does the opposite, right? So south pointed towards it, negative, right? And if south moving away from it, then it's positive, right? Now let me reverse the polarity. If north goes through it, it's again positive, and negative in case of the south. If I do the opposite way again, it does the opposite. So this is a crude example of a you can say an alternating generator, right? AC current generator, alternating current generator. There's so many names for it, so I simply call it an AC generator. So this is a linear AC generator. The ones we actually see in our daily lives, they're actually axial applications of the axial designs of the AC generators. This is actually a linear version. Linear generators also exist in some cases, not very common, but there are linear generators being used by the industry. So this is a linear generator, right? Why? Because the magnet or the coil is moving linearly relative to each other, right, in straight lines. While in axial generators we see circular motion or rotation of the magnets or the coil to generate electricity. I hope these things, some of the things are clear about Faraday law and electromagnetic induction, and how current is induced in a solenoid using magnetic field, changing magnetic field to be very exact. Thank you so much.